look at some examples because we talked about the standard normal distribution and z-scores last time, but we only looked at the examples from the textbook. We didn't really get to do any exercise problems. So let's take a look at some of these. So I picked a couple examples here. So the first example we're working on, and let's make sure I have the right number here. Yeah, number 16. So looking at number 16 over here, we are basically saying, okay, suppose there's a normal distribution that has a mean of 45 centimeters and a standard deviation of 10 centimeters. They're asking us to draw and label the normal distribution graph, find the range of data values that fall within 2 standard deviations of the mean, and then they want to know the percentages of data that fall between 15 and 55 centimeters and what percentage falls above 55 centimeters. So I've already copied over this problem over here. So you can see they're telling us that the mean is 45 centimeters and standard deviation is 10 centimeters. So I went ahead and put that information over here. Now, since we are not really doing graphing by hand, I just went ahead and did a normal curve over here. So basically what you do to graph this, and you guys will not be required to do the graphing, and that's why I kind of did this ahead of time. Basically, you will see I took our mean, which is right over here, and kind of use that as my center point. And then basically in increments of half standard deviations, I created the table over here. So 45 minus 5, which would be half of 10, gave us 40, and then keep subtracting 5 till basically I got down to 3 standard deviations below the mean, kind of using our empirical rule. So 3 standard deviations above, 3 standard deviations below, and then again took that 5 points and kept adding it till I got to 3 standard deviations above the mean. And the reason I did it in 0.5, like half of the count, was so that I could get a nice smooth curve. If I only kept 3 standard deviations, 2, 1, and then, of course, the mean, and then the same thing on the plus side, I was actually not getting a good, smooth, bell-shaped curve. And it's just because you need extra points so you can get a nice, smooth curve. And that's only the reason why I added those, half a points in the middle to get a better shape. And then this one over here, we're just using our normal dot distribution formula. The only difference is from when we were doing the calculations to when we are graphing, you will see instead of putting 1 in that last space for the cumulative, I actually use the word false. And that's what you do when you're graphing a normal curve. But again, guys, you are not expected to do any graphing. So don't, worry about, oh, how am I going to replicate this? And again, if you guys just wanted to see how the table looks, I'll go ahead and share this link with you if you just wanted to see how I came up with that graph. And then, once you have your table done, then you are literally just doing insert chart, and you go with a line graph, and then just make it a smooth line chart instead of, kind of like connecting the dots. You don't want to do little line segments. You want a nice smooth curve. So anyway, you have your general shape of the graph over here. Now, I tried to get, all of our markers in there, but the graph was not cooperating with me. So we'll do those ones by hand so that we can go ahead and say, where our mean and then 1, 2, 3 standard deviations are. So remember, your mean is going to be right in the very center. Let's see if we can make it a little bit of a straight line. So that's where your mean should be at 45. And then, of course, you go 1 standard deviation above, 2 standard deviations above, and then 3 standard deviations above, which should be, well, no, actually that marker right there is at 3 standard deviations. Okay, so that's good. And then we will be going 1 standard deviation below, 2 standard deviations below, and then of course the last one is 3 standard deviations. Okay, so let's put our numbers in. So this will be our mean at 45. And then of course, you keep adding 10 or subtracting 10 to get your standard deviation. So 45 plus 10 would be 55, which would be at 1 standard deviation above the mean. So this is 1 standard deviation above. 55 plus 10 would put us at 65, which would again be 2 standard deviations above the mean. And then 65 plus 10 would be at 75, which again, we know is 3 standard deviations above the mean. So in that same way, going to the left, 45 minus 10 would put us at 35, which is 1 standard deviation below. 35 minus 10 would put us at 25. That's 2 standard deviations below. And then of course, subtract 10 from 25, which is at 15, would be 3 standard deviations below. So this is that first part of our question where they said draw and label your normal graph over here. So we've taken care of that. Now our second question was, what range of data values fall within 2 standard deviations of the mean? So can you tell me what range of our data values fall within 2 standard deviations of the mean, which means 2 standard deviations below and 2 standard deviations above? So what will those range of data values be? So your mean is right in the center. If you are going 2 standard deviations below and 2 standard deviations above, what are we looking at? So I can see Michael and Terry, you guys have shared an answer with me. Anybody else? Yeah, so very nice, guys. 2 standard deviations below would be right over here at 25, and then 2 standard deviations above the mean would put us at 65. So very good. Your range of values would be going from 25 to 65. All righty, perfect. So that's going to be our second answer here. So from 25 to 65. All right, part C is asking us what percentage of data values fall between 15 and 55 centimeters. Okay, so as you can see, our 15 is right over here. So that's 3 standard deviations below. And they're saying going from 15 to 55, which is this year. So they're basically wanting to know what percentage of data values are falling within this section of our normal curve. And for this one, you guys may want to, basically look at that little chart we had done where we had all the breakdowns. So, kind of like this one over here. So what percentage do you think of our data values fall from 15 to 55 centimeters? And remember how last time I had shown you guys there's multiple different ways. So, pick whatever way you find the most convenient to kind of help you out. It won't superimpose on it, so I can't really superimpose it on there. All right, I can see one answer coming through. Terry, very nice, very good. So as you can see over here, and I'll try to do this on the graph, which is in the textbook section. So if you look at how many sections we basically went from, where that 3 standard deviation below is, because that's where our 15 was. And then you are going 1 standard deviation above the mean. So this is the section that we are looking at. So the only difference that's going to be is we don't actually have this section included because you are starting at 15, which is at 3 standard deviations below. So you will leave this little section out. And then of course you are leaving this one, and this section out also. Yeah, Terry, I was going to say, very nice. Yeah, that you kind of have to just remove that little tail out and you are good to go. So basically you can add these numbers together if you wanted, or you can say, you know what, if I had the whole left side of my, the name just flew out of my head, normal curve. If I had the entire left side of my normal curve, that would be 50%. And then I have this little section here, which would be 34%. Well, together that adds up to 84%. And I'm guessing, Terry, that's kind of what your initial thought was? Maybe? Okay. However, like I said,
all of the parts together, and then
oh, you added
it
them.
looked
Okay,
like it was
okay.
included, the 0.15.
Okay. Okay, got it. Yeah, and like I said, that's one way of doing it for sure. So now we know, well, actually, I don't have the whole left section because I didn't really have this guy in there. So then just go ahead and subtract that 0.15%. And I think it was, what was it, Terry? 83 something, 83.85. Yeah, perfect. And that's what that percentage is going to come out to be. Does that make sense, guys? Question on this one? Okay, so I'm going to save this, but we will need to erase these lines over here. I will leave that answer. Oops, sorry. We can bring that over here. So that will be 83.85%. And again, like I said, you can do it as 50% plus 34%. And then subtract 0.15% from it. Or you can do it in a different way. So for now, I'll just leave that in there so you guys can at least have some idea of the calculation we did. Alrighty, so that was part C. Part D is asking us what percentage of the data falls above 55. So let's see if I can get this guy to line up again. Okay, so we are saying what percentage of data falls above 55. So of course you can see when they're saying above 55, we're talking about this section over here. And since they are saying above 55, you are of course going all the way to the tail end. So what do you think that would look like? Okay, and I've got Terry's answer coming through. Anybody else? What do we think about that? So above 55, what will that look like? Well, this one should be fairly simple because you are going all the way till the tail end. So if you are going till the tail end, you're of course including everything to the right-hand side. So coming back to our little diagram over here again, your 55 was again at 1 standard deviation above, and they're saying going above 55. So you're including that whole section here. Now there's again 2 ways of doing this. You can definitely add each one of these individual numbers, or we can say, you know, again, that right half is 50%, and the only section I'm not including in the right half is this guy. So subtract that 34% from 50 and you'll get 16%, or like I said, just add the 13.5 plus 2.35 plus 0.15 and you will get the same result. Yeah, Michael, very good. So this guy will come out to be 16%. And again, I'm just going to say for now, we did 50 minus 34% in this case. All righty. Now, the last question is actually not part of 16, but it is part of the question. So it's asking us to calculate the z-score, and I actually got that from this one over here. So it's basically telling us for the distribution in problem 16, calculate the z-score for the data value of 32 centimeters. So I just, since we were working on number 16, I just included this guy in there. So calculating the z-score, basically you have that formula, which again, we looked at it in the last section also, and then you have it right here. So your z-score is where you basically take your data value, subtract the mean from it, and then divide that subtraction by the standard deviation. So take a minute and tell me what will this z-score come out to be here for the value of 32. So what will our z-score for 32 centimeters come out to be? And that basically just tells you, remember that z-scores are basically telling you standard deviation. So they're telling you how far away from the mean they are going to be. So while you guys are working on that, your 32 would be between 30 and 35, closer to 30. So let's say maybe somewhere over here would be your 32. So if your data value is below the mean, what will your z-score be, positive or negative? Michael, why did you get such a large number there? Yeah, Terry, very good. Sabrina, yeah, very good. So remember, if your data value is below the mean, your z-score has to be negative, because that's again your standard deviation. It's just telling you how far away from the mean you are. So you will end up doing 32 minus 45, get that answer first, and then divide it by 10. So
my calculator did something weird.
say that again, Michael.
My calculator did something weird.
Oh, it did something weird. Okay. Yeah, so that's what you should end up with. Now I'm just showing you, you know, by hand, but you can type that whole thing in your cell and let Excel do the calculation for you. So let's go ahead and put that in our cell over here. So basically, since we don't have anywhere that we have posted 32, so I'll do equal to, and then in parentheses, I'll do my subtraction. So that would be 32 minus our mean of 45. Close your parentheses and divide by the standard deviation of 10. And of course, you will see you will get the same result with Excel as well. All right, anybody have questions on this example over here? Okay, I see something coming through. Yeah, I did, but I can share it again, Terry. Let me copy that link one more time. So again, guys, here is the link for this document. If you guys wanted to keep this for reference, I just sent the link through chat again. Alrighty, folks, let's take a look at one more example before we move on to our confidence interval. And this is number 20. Okay, so number 20 over here, kind of the same thing, but just dealing with, decimals instead of whole numbers. So this one over here, again, they're telling us this normal distribution has a mean of 26.1 grams and a standard deviation of 6.5 grams. Again, they're asking us to draw and label the graph. What percentage will fall above 32.6 grams? What percentage will fall below 15 grams or greater than 36.7 grams? And the last one is what percentage of data is less than or equal to 20.8 grams. So that's the calculation that we are doing. So again, in our sheet, this is going to be the second to the last sheet. So you can see at the bottom, it says section 3.6, number 20. So I pretty much did the same thing as I showed you before. So I took our mean and our standard deviation of 26.1 and 6.5 respectively and did the same thing, took half of the standard deviation away. So basically taking half of 6.5 and then subtracting that from the mean, which gave me 22.85, and continuing with, increments of half. I kept subtracting that, which if we take half of 6.5, what does that come out to be? 3.25. So that's, by how much I keep changing it till I came down to 3 standard deviations below, and did the same thing on the positive side till I came up to 3 standard deviations above, so that I could get a nice smooth curve on my graph over here. So pretty much the same thing that I did in number 16, I did the same thing over here to do our graph for this guy. So we have our little graph here. Now, as you can see, these are not happy numbers, right? Because you are working with decimals. And then as we did the increments, we end up with all these looking numbers, which are quite different from what we have seen so far in all the examples. So again, as we are labeling this, can I try and get this on the same screen? Almost. All right, so again, in the very center will be our mean. Well, somewhere over here. And that is at 26.1. So that's our mean. Let's see, 1 standard deviation away is putting us at 32.60. So somewhere over there, 2 standard deviations is 39.10. So this guy over here, and 3 standard deviations away is at 45.60, which should be that last dot that we have over there. Then 1 standard deviation below was at 1960. So that will be this guy over here, just shy of 20. 2 standard deviations below was at 1310, which will be this guy here. And then, of course, the last one is going to be our 3 standard deviations below. So that one was at 660. And this is 3 standard deviations below. 1310 was at 2 standard deviations below. And then 1960 was at 1 standard deviation below. Okay, then we had 3260 on the other side, so that's +1. 3910 was at 2 standard deviations above, and then 4560 is 3 standard deviations above. Okay, so now that we have all our labeling done, they are asking us what percentage of the data falls above 32.6 grams. So 32.6 grams is your 1 standard deviation marker. So that's this section over here. So greater than or falls above, you are of course going all the way till that tail end again, guys. So 1 standard deviation above and going all the way to the right tail, what percentage of our data values will fall in that little section? And this is basically the same thing we just did in the previous example. So if we go back up, oh, sorry. Where's our little chart over here? There we go. What percentage is falling in that section as you go from 3260 and above? And that is 1 standard deviation above the mean. And, of course, beyond that. What percentage are we looking at? Terry, perfect, very good. So if we're talking about 1 standard deviation above, we're basically saying this is where our 3260 would fall in our example. And they're saying, anything that is above that number. So that of course includes everything in this area. So it's the same thing. You either add 13.5 with 2.35 plus 0.15, or as I was showing you before, you can do 50 minus 34, which would also give you the 16%, because we could say, well, we're looking at the right half, but not including the 34 section. So take that guy out and it leaves you behind with the 16, sorry, not 60, 16%. So that's what we will have over here. This was part B. So 16%, and again, I'll just say 50 minus 34. Okay, the next one is asking us, what percentage of the data is below 15 grams? Okay, so below 15 grams. So 15, of course, has to be halfway between 10 and 20. So halfway between 10 and 20. And I'm kind of eyeballing this guy, so if I'm a little off, I apologize. And then below 15 grams and greater than 36.7. So 36.7. And again, I am really eyeballing this. Maybe somewhere over here. So this one would be 15, and this one would be 36.7. So if they're saying below 15 grams, then, of course, we're talking about this whole section. So it goes all the way till the tail. Below 15, and then greater than 36.7. So then, of course, we're talking about this section here. Yeah, Terry, go ahead.
Are we doing any kind of subtraction like on the 13.5 because it's hitting in the middle of the second?
So, because again, we're kind of eyeballing the location. You don't want to estimate anything. You want to have exact answers. So this is where, if we were doing this by hand, then we would want to do Z-scores, first figure out where they are Or if you remember, for these ones, we can actually use these formulas that we had. Oh, sorry. 1 second, let me get back over here. So because these numbers are not exactly aligning with 1, 2, or 3 standard deviations, right? Because as you can see, they kind of fall in between. You don't want to use these percentages that we have over here in this little chart, because this one works perfectly for if you're right at 1, 2, or 3 standard deviations away. So for these types of examples, which kind of fall in between, this is where you want to use either this little calculator that I showed you last time, the online stat book one, or you want to use these built-in calculations. So this would be the one that we would be looking at for this part B over here, because we are saying below 15. So that would be this section over here. And then the other one is saying above 36.7, which would be this. So you either use these built-in functions here with the norm dot distribution, or, and let me save that very quickly, or you want to use this online stat book calculator. And let me share that link again with you guys. I did add these links in your My Open Math under homework, so you guys should be able to see that. And I just send the link through chat, so hopefully you guys can do that also. So I'll show you very quickly how to do this with the norm.distribution function, and then we can verify our answer with the online stat book calculator also. So this is where, again, if you can see the sheet that I'm sharing, I'm typing that in over here. So that would be our norm dot distribution. And then for this one, we start with our lower number, which will be 15 in this case, comma, your mean is 26.1. comma, our standard deviation, which is 6.5. And then this is where for that last argument, we put a 1. Okay, then you are going to do plus 1 minus, and then we do the norm dot distribution function again. So norm dot distribution, this time we go with the higher value, which was 36.7. Again, comma, the mean, 26.1. comma, standard deviation 6.5, and then again for the last argument we put a 1. And by default you are going to get a decimal answer, guys. Terry, what are those numbers? Just your z-score?
I put them in the graph. The mean of 26.1, the standard deviation 6.5, and then the above and below on my on that chart that you just shared with us.
Yeah.
And then I put above 36.7.
Are you sure this is a reaction to what happened with Eva? I mean, she lied to you for weeks.
Dad, I am not afraid of being deceived.
Brooks, something's going on at your end, buddy.
It's not Kramer. I know it.
So that's how I got that answer. So I don't know what I did. I didn't put it in.
Okay,
percent,
so you need to actually do the outside calculation. One thing I wanted to show you guys is right now, since the answer is showing up as decimal, if you format it as a percentage, it will convert that to a percent. So you can, get that. So yeah, Terry, let's take a look at this guy over here then. So for this one, of course, you're putting in your mean and standard deviation, which you told me you did that. So 26.1, 6.5. Okay, and then of course, we don't want these numbers in here. So this is where you're going to be putting in that information for the 15 and the 36.7, Terry. So you will select the outside. And then we will say outside of 15, and then the upper limit was 36.7. And you should see it highlights those exact sections that we want. And then when you say recalculate, it gives you your decimal percentage. And you will see again, as you convert it to, from a decimal to a percentage format, that will of course become 9.53 as we move our decimal 2 places to the left. If I can get that whole thing. So this is what we should be coming up with, and it's kind of overlapping over there. Okay, let's do this. So that's what our percentage should come out to be, 9.53%.
52.
All right, perfect. And then the last one over here is asking us for what percentage of the data is less than or equal to 20.8 grams. Now our 20.8 is going to be literally just a hair away from 20. So let me see if I can kind of get something going here. So say somewhere over there would be 20.8. And again, they're saying is less than or equal to 20.8. So again, you're actually looking all the way till the tail end because it's less than or equal to. So this is the section we are looking at, and this would be our 20.8 grams. So again, for the 20.8 grams, since that is not exactly at a 1, 2, or 3 standard deviation, you again want to use the norm dot distribution function for this one as well. So this is where if you are talking about below, then you just directly use your norm dot distribution function. So our data value is 20.8, comma, our mean is 26.1, comma, standard deviation 6.5, and then again for the last argument you put 1. And you can see this is coming out to be 20 something percentage. So again, we'll format that as a percent, and you can see that comes out to be 20.74. Now again, if you wanted to use our little online stat book, then you are just get rid of these guys and you are just going below because that's less than, and just put in your 20.8 over here, and you will see this guy again came out to be 20.74 as our percentage. And I wanted to actually show you even for that first one here where we did the 16%, if you also used your norm dot distribution in this, you would still get an answer. It would probably be a little bit more accurate than that. So I'm going to show it to you on the box to the right here. So if you did, remember when you're doing above, and let's come back over here. When you're doing above, remember you have to use the 1 minus norm dot distribution function for that case, because by default, the norm dot distribution always gives you the area to the left of the number. So if you want to go to the right, we do the 1 minus. So this is what we would be using. So over here in my spreadsheet, I will do 1 minus norm dot distribution, and then our number was 32.6 grams. And then again, the next argument should be mean. The one after that is standard deviation, and then for the last one we put a 1 in there. So you will see that gives you a little bit more of an accurate answer, which is coming out to be 15.87 instead of just using the empirical rule, which gave us the 16%. And again, you can use your little online stat book calculator also. So let's get rid of this and we were doing above 32.6, and of course you will see that ends up giving you the 15.87%. So just as a disclaimer, you guys can use the built-in function norm.distribution if you want, or if you're like, you know what, I don't even want to mess around with that, I just want to use this calculator here. You can see they work on the same calculation. So it'll give you the same thing. The only difference would be when the question specifically asks you to use the empirical rule. Please stay with this little guy here. Oh, where did he go? This is what you would be using if they specifically say empirical rule. Okay. All right, fellows, any question on this example over here?
Can you explain again why you went with 0.5?
Oh, because that just evenly breaks it up, because, you know, if you only did 1, 2, 3 standard deviations, the curve actually does not come out very nice looking. It doesn't have that bell shape. So I just broke it up into halves after that.
Okay.
So it just
that
gives you
just
a better
helps
shape.
for the image of the bell curve. But if we were doing the assignment, we wouldn't have to necessarily do that, right?
No, this table, like you saw, we didn't really need this table for anything. This was just what I created so that I could show you what that bell curve looks like. So I didn't have to, you know, keep drawing those wonky looking bell curves by hand.
Okay, thank you.
Yeah. All right, very nice. Okay, so let's clear this up. So the last part we want to talk about here, guys, in this chapter is confidence intervals and margin of error. So we did actually talk about these in section 3.1, but we didn't actually talk about how to calculate the margin of error or the confidence interval, other than you know, just adding and subtracting numbers, which is pretty much what you will be doing over here. So just some terminology to get you started out with initially. Now, when we're working with confidence intervals, basically the idea is, you know, when we take a sample, because obviously it's not going to be easy to survey a whole population or, you know, talk to the whole population. So the idea is, whatever information we can gather from the sample, we want to apply it to the larger population. And we want to say, you know, if this is what my sample is telling me, and I have a really good sample which represents my population well, then I should be able to make that inference that if the sample is saying this, I can apply this to my whole population also. So here they're just talking about an example of what if we wanted to know what is the average height of 10-year-old kids who are living in the United States. Now, obviously, we cannot talk to all of them. So we would do a small sample, which would be a good representative, you know, for our population. So basically the idea is, let's say we took 25 randomly selected 10-year-olds and we calculated their height, and their mean, the sample mean came out to be 54.5 inches. This sample mean is what we would call as a point estimate. Okay, so just a new terminology, but all that means is you are looking at the sample mean for this specific group of kids that we, you know, selected as our random sample. Now, however, what if we took another group of 25 kids and measured their height? You know, of course, your mean would come out to be slightly different, because now you are looking at a different, you know, group of kids in that case. So remember, this happens every time we change our sample. So if we did like separate groups of 25 kids, you know, from different areas and measure their heights, each one of those groups of 25 is going to give us a different sample mean. And this is where, you know, we had discussed sampling error comes into play, because, you know, your sample changes, your numbers are going to change. So to get a more accurate estimation, and in this case, we're talking about the height of 10-year-olds, this is why we do confidence interval, because we can say, because of that sampling error, our margin of error is going to be, you know, whatever, 2 inches or 5 inches, or, whatever that sampling error, based on that, whatever our margin of error might come out to be. So based on that, we then create our confidence interval, because then we can say, we are 95% confident that 10-year-olds in America are going to fall between this range of height, and whatever that range comes out to be. So that's where this idea of the confidence interval comes in, so that we can, make space for some of that sampling error that happens as you keep changing your sample. So that's your point estimate, which basically references the sample mean. Your confidence interval is just telling you between what heights we can say most of the, population of our 10-year-old children is going to fall. Okay, then the next one is, of course, if you are constructing a confidence interval, you need to know what your point estimate is, which is your sample mean. You need to know what your standard error is, and your standard error is basically, again, an estimate for your standard deviation that is calculated based on your sample data and what your sample size is. So your sample error is basically going to be your standard deviation based on your sample data and whatever your sample size is. And then the other thing you need to know for the confidence interval is what is the level of confidence that we want. And remember, I had talked about this again back in 3.1. Normally, your confidence interval goes from 90%, 95%, or 99%. Now, those are the 3 most common ones. And even out of those 3 most common ones, 95% is kind of what most confidence intervals we use. So you can have 90%, 95, 99%, but we're kind of focusing only on 95% right now. So when you're working with the 95% confidence interval, basically remember, if you were looking at this at the normal curve, that would be that middle 95% of your normal curve. And remember, from the empirical rule, we know that that's going to be 2 standard deviations within your mean, where you have the 95%, because that's your second category. Remember, it starts at 68% in the middle, 95%, and then it goes out to 99.7%. So that's that middle 95% that we are talking about. So empirical rule tells us that 95% is approximately 2 standard deviations below and above the mean. But again, if we were to do a little bit more of an exact calculation, it exactly actually comes out to be 1.96 standard deviations from the mean. So from the empirical rule, we say it's 2 standard deviations, but when we get into a better exact calculation, that actually comes out to be 1.96%. So that's your 95% confidence level. So those are the 3 numbers we need: the point estimate, the standard error, and then our 95% confidence level that we will be using over here. So let's take a look at how this looks like. So this is what your graph would look like. This is based on the empirical rule. So here's your mean. This is 1 standard deviation above. This is 2 standard deviations above. This guy, of course, would be 1 standard deviation below and 2 standard deviation below. And this represents 95% of your data value. So this is that level of confidence that we are also using in our example over here. So now you can kind of see, going back to our 10-year-old kids with their height, we're basically saying our point estimate for the height is 54.5 inches, which was our sample mean. We are saying our standard error, which is basically your standard deviation based on this sample, is 1.75 inches. We want to estimate what the middle 95% of values are going to be. So this is where we are talking about our confidence interval. So this is where you take your point estimate or your mean, and then you add and subtract that 1.96, which is that exact standard deviation for the 95%. And then your standard error, or basically your standard deviation for this specific sample. So that's your calculation over here. So just to kind of write it out, this would be sample mean plus or minus, then this is your 95% standard deviation. And that is being multiplied with your sample standard deviation. So this is, based on that exact number. So this number will always be 1.96. And then these numbers will keep changing based on what example you are looking at. So this example, our standard mean was 54.5 inches. Our standard error for this guy was 1.75 inches. And then this number, of course, stays the same. So that's the calculation you are doing. So go ahead and multiply these two numbers first, because multiplication comes before addition or subtraction. So you'll multiply first, and then whatever that answer comes out to be is actually your margin of error. So this 95% standard deviation multiplied by the samples standard deviation, that's your margin of error. And then you're adding or subtracting that from the sample mean, and that's how you come up with your confidence interval. And you can see, so we are basically saying we are 95% confident that all the 10-year-olds in America fall within the height range of 51.07 inches to 57.93 inches. And you can see that conclusion kind of mentioned over here. So we are 95% confident that the true average height of all 10-year-olds is between 51.07 and 57.93 inches. And then you can kind of see they're talking about if you did repeated samples, of those groups of 25 kids, and the 95% confidence interval was, calculated for each of those samples that you did, then basically about 95% of the intervals would contain that true, population mean, whatever that comes out to be. And we're saying about 5% of the intervals would not contain the same population mean. So about 5%, because we are keeping that 95% confidence interval, the remaining 5% would basically fall outside of that range of, 51.07 to 57.93. So that's the calculation you really need to remember, is this one for the confidence interval. And then down here, they talk about the margin of error. So for the margin of error, like I said, is basically going to be that 1.96 number multiplied by the standard error for whatever the example might be. So this guy would be, again, just using our example here, basically look at that. It's that same number, 1.96 multiplied by your standard error. So that's 1.96 times 1.75. And that's the same thing over here, which gives us 3.43 inches. And that's your margin of error. So from that mean of 54.5 inches, we're basically saying give or take 3.43 inches. And that's where most of the 10-year-olds' heights are going to fall. And that's what that margin of error basically tells you. So I've got a couple examples for us to work through here. So let's take a look at that. And that's going to be the very last sheet on this Google Sheets that I shared with you guys. So this is numbers 30 and 32. And I've included the formulas down here at the bottom. You will see those are the ones in the color boxes. So you can kind of see how each one of those calculations is done. So we're talking about number 30. And I can show you that over here also. So number 30 is talking about scores on a certain quiz are normally distributed. In a sample of 25 students, the mean score was 14 points and the standard error estimate of 2 points. They're asking us to calculate the margin of error and then the 95% confidence intervals, and then, interpret what that confidence interval basically tells us. So coming back over here. So remember, your point estimate, guys, is the same thing as your mean. So this one here will be the same thing as the mean. And you can see they're telling us our mean score was 14 points. So this is going to be 14 points. Your standard error, remember, is basically for this sample, what is your standard deviation, which they're using the term standard error, and that's going to be 2 points. So your standard deviation actually is also going to be the same number as 2 points. And the reason why I'm not using 1.96 over here is because they're telling us this is normally distributed. So since they're telling us this is specifically normally distributed, we're just leaving it at that empirical rule value and not doing it at, you know, the same calculation. So this one actually is going to be a little bit different because they're telling us the quiz is normally distributed. So this is actually going to be just straightforward, no calculation. That means our margin of error is actually only going to be at 2, which is the same as our standard error in this case. So when they tell you it's normally distributed, honestly, you're not using any of these calculations here that we looked at. So you are not doing this, you are not doing this when they tell you it's normally distributed. There we go. So in this case, you are just keeping that same error as your margin of error. So when you do your confidence interval, it's basically going to be the point estimate, our mean, minus the margin of error and plus the margin of error. So this will basically be for the lower boundary, where you take your mean and subtract the 2. And then for your upper boundary, you will take the mean and just add the margin of error or the 2. So your confidence interval is basically going to be going from 12 to 16. And all of this, guys, because they're specifically telling us this is normally distributed. So very different when they don't tell us that. And that's why I picked number 32 over here. So if you look at number 32, they're telling us a researcher works on a study and found that the sample mean is 35 point basically 40 cents, $35.40. And the standard error of estimate is 75 cents. What is the margin of error for the 95% confidence level? And then of course, what is the 95% confidence interval for the true mean? And then interpret the results. So this one you will notice they're not telling us this is normally distributed, right? Nowhere in the example normal distribution is being mentioned. So that actually means this is where we are going to be using these calculations. So since they don't tell us this is normally distributed, these are the two formulas you are going to be using. So you will be using this one and this one to calculate our confidence interval and margin of error. So let's come back to our sheet here. So point estimate is your sample mean. So this will be 35.4. Or if you want to format that as dollar amounts, you can, because that's how they're giving it to us in the example. Our standard error is 75 cents, so 0.75. And again, you can format that into dollars. Now here, because they specifically did not tell us this is normally distributed for your standard deviation, you will actually use 1.96. So you're not using the empirical rule. You are using, and I've mentioned that right here in the last section over here. So you will be using 1.96 as your standard deviation. So now to calculate our margin of error, you are going to do that 1.96 multiplied by the standard error. So using this formula, so this will be 1.96 multiplied by our standard error, which as you will see will come out to be 1.47. And then when you calculate your confidence interval, for your lower boundary, you will do your point estimate or your sample mean, and subtract the margin of error from it. And when you do your upper boundary, you take your point estimate and add the margin of error. And you will see this guy now comes out to be a confidence interval of $33.93. And then for the upper boundary, we had $36.87. And that's how you write out your confidence interval. So just the contrast between the two examples of one where they're telling you it's your normally distributed, and the other one is not telling you it's normally distributed. And honestly, the difference comes right over here in how you write out your standard deviation for the 95% confidence interval. So in the normally distributed one, we kept the empirical rule value, which is 2 standard deviations. And then for the standard deviation, when they didn't tell us it's normally distributed, we went with the exact calculation, and that was the 1.96 instead of 2. So honestly, that's the difference that we're coming up with. Questions on these two examples here, guys? Yeah, go ahead.
So what, okay, so just to recap, it's a, above it was a normal deviation, or you were saying a normal deviation or a normal,
Yeah, because it's normally
Deviation.
distributed.
okay. So the one above is normal because, well, it says normally distributed, which means the same as using the standard deviation, which is the 2.
So using the empirical rule, yeah.
Empirical, okay. So we use empirical when it's.
Yeah, I
it
think
says
I actually
normal.
misspelled that, but yeah. Right, so you're using the empirical rule here, but then for this one, you are using the exact calculation.
Okay. Thank you.
And again, remember, guys, in the empirical rule, and let's go back over here. If you go up where we first introduced the empirical rule. Right here, you can see this is where they told us that the middle section was 95%. So this is where we are getting that from. And you can see again, that middle one is where they tell us it's 95%. So that's what you are using for when they tell us it's normally distributed. We went with this percentage, and that is exactly 2 standard deviations above and below the mean. So that's why we are using 2 in that first example, number 30. So that's the reason why we have 2 over here. But then in the second example, there is no mention of this being normally distributed. And that's why we go with the more exact number, which was the 1.96. Any other questions coming to mind, guys?
I will in about 2 hours.
Okay, that's fine. No problem at all. So that was the last part we needed to talk about, guys, in chapter 3, basically. And you can just kind of see how they're just talking about the last part over here. They're just mentioning, since the point estimate is our best guess for the value of the parameter, because, again, your point estimate comes from the sample, and we're trying to generalize that for the entire population over here. We're basically saying it makes sense to build a confidence interval around that value of, what your sample mean is. Now, your standard error, which is, of course, remember the standard deviation for that specific sample, the standard error, which is a measure of the uncertainty associated with our point estimate, it provides a guide for how large we should make the confidence interval. So these are all kind of, based on one value helping the other one, or, trying to give us more sense of what's going on. So when the sampling distribution of a point estimate can be reasonably modeled as normal, we know that from the exact calculations you are going to get 1.96 as your standard error, your standard deviation. So in that case, we are saying, okay, yeah, so based on that, we can be 95% confident that our interval that we come up with is going to be, close to that true value, what it should represent for the population. But again, we are kind of going on estimates and what the sample is telling us. So we can never say, guys, we are 100% confident that this is what our number is going to be. And so that's why you will see we are not using the 99% confidence interval either. We try to kind of stay more at a reasonable amount. And I think 95% is a good number to say, yes, we know there can be room for error, but we are still giving you a pretty high level of confidence with 95%. So we're not going all the way to 99 or 100%, but we're saying, yes, there's room for error, because this can always happen with statistics. But even then, we can be 95% sure that within these numbers, you will find your true value. And that's what you are doing with these confidence intervals. So as I was telling you before, if you look at any study or poll, they should always mention what the margin of error is. So that lets us know that, give or take of these numbers is where your true value will lie. And that's what they're basically talking about here in the last section, is just kind of wrapping that up. So you will see some examples, and I think, Terry, you and I were looking at that in your homework before, where they will just ask you to find that confidence interval or margin of error. So work through that. If you guys have any questions, send me an email. As I was telling you guys before, I do have a meeting I need to get to, so unfortunately I can't stay back and answer any questions. But if you will email me as soon as I'm done with my meeting, I will start sending you guys replies, okay? All right, everybody, I will stay for a couple minutes to answer any questions that you might have. But otherwise, have a great, wonderful weekend. And then I will be seeing you on Monday for our Chapter 3 exam.
Thank you.